Section: Introduction. In this section, we discuss learning from feedback, which is a common method used to adjust the behavior of artificial agents to align with human preferences. Recently, there has been a rise in using reinforcement learning from human feedback to fine-tune large language models. The traditional way to fine-tune these models is by learning a reward signal using the Bradley-Terry model and then applying reinforcement learning based on this signal. However, a new model-free approach called direct policy optimization, DPO, has been introduced, which achieves the same results as the traditional method without the need to learn the reward signal. Two new approaches have been proposed that aim to optimize against preference probabilities directly, rather than using the Bradley-Terry model. The first approach, Identity Preference Optimization, IPO, optimizes preference probabilities against a fixed data distribution using an offline contrastive loss. The second approach, Nash MDPG, aims to find a Nash equilibrium with respect to preference probabilities through online policy gradient updates against a regularized policy. These two algorithms have different characteristics but are both effective in their own ways. Our work focuses on bridging the gap between IPO and Nash MDPG to create a new class of preference optimization algorithms. We identify key differences between the two approaches, such as their use of offline-online data and the nature of their equilibria, and combine their strengths to propose online IPO, an online version of IPO. Additionally, we introduce a new algorithm called IPO-MD, which combines the best aspects of both IPO and Nash MDPG by interpolating between offline and online variants using the lagged data distribution of Nash MDPG. We conduct experiments to compare these algorithms in various applications, providing insights for practitioners. In the background section, we introduce the preference optimization problem in Bandits, where a preference function specifies pairwise preference probabilities between elements. The goal is to find a policy that selects preferred actions, and we explain how this can be formalized in different ways. Actions are sampled from policies, and the preference distribution is defined based on the preference function. We also discuss the data model, including offline and online settings, initial policies, and trust regions for policy optimization. Our paper unifies and contrasts different approaches to preference optimization, offering a comprehensive overview of the topic. Section Summary. In this section, we explore the concept of learning from feedback to align artificial agents with human preferences, particularly focusing on reinforcement learning from human feedback for fine-tuning large language models. We discuss traditional methods like learning reward signals under the Bradley-Terry model and reinforcement learning, as well as newer model-free approaches like direct policy optimization, DPO, that bypass learning reward signals. Additionally, we delve into recent algorithms such as Identity Preference Optimization, IPO, and Nash MDPG, which optimize against preference probabilities directly, leading to the proposal of novel preference optimization algorithms that combine the strengths of existing methods. Section: RLHF with a Bradley-Terry reward model. In this section, we present our approach to preference optimization using a Bradley-Terry reward model. Our method consists of two main steps. First, we fit a reward model using the Bradley-Terry model, where we approximate preference probabilities using a logistic function. We then learn a reward function by maximizing the likelihood in this model based on observed preferences. Next, we aim to maximize the expected reward under a given policy while adhering to a KL constraint against the initial policy. This is done by reparametrizing the optimal reward in terms of the optimal policy and maximizing the resulting objective with respect to the policy. We also introduce direct preference optimization, DPO, as an alternative to the previous approach. DPO bypasses the learning of a reward function by reparametrizing the optimal reward in terms of the optimal policy. The mathematical derivation shows that DPO yields the same optimal policy as the previous method, which is a regularized optimizer for the reward model. Additionally, we propose sequence likelihood calibration, SLIC, as another alternative to the initial method. We refine the SLIC loss by normalizing the policy probabilities with reference policy probabilities to obtain a regularized offline loss. Furthermore, we introduce identity policy optimization, IPO, to address potential issues with DPO. IPO aims to directly optimize preference probabilities against a fixed policy, ensuring regularized policies by discouraging large deviations in log probability ratios between actions. Moreover, we present Nash MDPG, which interprets the optimization objective as a two-player game where policies are selected to maximize payoffs. By finding a Nash equilibrium in this game, we aim to achieve more robust policies that are not overly specific to the data-generating distribution. The Nash MDPG algorithm allows for a trade-off between self-play and sampling from the data distribution through a parameter beta. Section Summary. In this section, we introduce a preference optimization approach using a Bradley-Terry reward model, which involves fitting a reward model through the Bradley-Terry model and then optimizing policy to maximize the expected reward under a KL constraint. We also explore alternative methods such as direct policy optimization, DPO, sequence likelihood calibration, SLIC, and identity policy optimization, IPO, to address issues like under-regularization and convergence to deterministic actions. Additionally, we propose Nash MDPG as a two-player game approach to finding robust policies that balance between self-play and sampling from a data distribution. Section: Comparative discussion of preference optimization algorithms. In this section, we will discuss the differences between preference optimization algorithms. We have several algorithms to compare: DPO, SLIC, IPO, and Nash MDPG. Each algorithm has its unique characteristics. Let's start with the contrastivity aspect. IPO is a contrastive algorithm that categorizes a pair of preferences into positive and negative examples and updates the policy based on both samples. On the other hand, Nash MDPG is not contrastive. It only updates the policy probability of the sampled action directly. Generally, contrastive algorithms can be more efficient in using data by utilizing both samples in each policy update. Next, let's consider offline and online data usage. IPO is an offline algorithm that works with a fixed dataset, while Nash MDPG is an online algorithm that uses sampled actions from the current estimated policy and a geometric mixture. Working with offline datasets can be beneficial in some cases, but gathering data online can help with effective regularization. Regularization is important to prevent learning bad policies that deviate from the data distribution. Moving on to equilibria, IPO has a supervised objective with a fixed data distribution, while Nash MDPG is a game-theoretic algorithm where the loss function and data distribution change as the estimated policy changes. Nash MDPG allows for sampling from a mixture distribution between the policy and the data-generating distribution, which can improve performance. To bridge the gap between offline IPO and Nash MDPG, we introduce a new variant called online IPO. This variant uses an online data distribution. The online IPO population loss is derived by replacing the static data distribution with the data distribution generated by the current policy. This loss helps analyze the performance of the algorithm. In conclusion, online IPO aims to find policies that are stationary by considering a fixed point condition. The minimizer of the online IPO objective is the Nash equilibrium of the preference game optimized by Nash MDPG. This connection highlights the importance of regularization and contrastive updates in improving algorithm performance. Section Summary. In this section, we discuss preference optimization algorithms, highlighting the contrastivity between IPO and Nash MDPG. IPO is a contrastive offline algorithm that labels pairs of preferences and updates policies based on both positive and negative examples, while Nash MDPG is a non-contrastive online algorithm that updates policies based only on sampled actions. Additionally, we introduce online IPO as a variant that bridges the online-offline gap by utilizing an online shifting data distribution, showing a theoretical connection between online IPO and Nash equilibria for preference optimization. Section: Online DPO. In this section, we examine whether online versions of DPO and SLIC are related to the regularized game as in the equation for the payoff. We investigate this for online DPO in Sec. Online DPO Sup. Lem. Online DPO KKT provides conditions for the stationary point of the regularized game and online IPO to be a stationary point of online DPO. However, these conditions are challenging to meet. For instance, THM2-class Nash is not DPO solution states that except for uniform preferences, P1 suc 2 equals 1/2, there is number 2 action problem where the condition is satisfied. Hence, except for the simple uniform preference case, online DPO and online IPO differ in objectives when the number of outcomes is 2. Regarding stationary points of online DPO, we demonstrate that under the assumption of the Bradley-Terry model, the RLHF solution, EQ, RLHF closed form, is a stationary point of online DPO, THM, online DPO KKT, aligning with that of offline DPO. After establishing a link between online IPO and self-play, we consider enhancing self-play by using regularized policies to generate data, similar to how Nash MD optimizes preferences against a regularized opponent. By adjusting the data distribution in the IPO loss using a geometric mixture between online and reference policies, we introduce a new set of algorithms called IPO-MD. This family of algorithms corresponds to the policies for Nash MDPG. The algorithm IPO-MD, beta, interpolates between online IPO, self-play, when beta equals 0 and a variation of IPO that aims to improve against a fixed policy pi-ref, when beta equals 1. We compare Nash MDPG with IPO-MD and observe that Nash MDPG is on policy, updating based on actions sampled under the current policy, while IPO-MD is off policy, updating based on actions sampled under pi-1 beta, pi-ref, beta. The fixed points of IPO-MD, beta, coincide with those of Nash MDPG, beta, although their gradients differ when beta greater than 0. The fixed points of both algorithms align with the regularized game described in the equation. Section Summary. In this section, we investigate the relationship between online variants of DPO and SLIC losses with the regularized game. We find that online DPO and online IPO differ in objectives when the number of classes is 2, except for the uniform preference case. Additionally, we introduce a new algorithm, IPO-MD, which interpolates between online IPO and offline IPO by modulating the data distribution using a geometric mixture of online and reference policies. Section: Experiments. In this section, we will present our findings from experiments where we fine-tuned large language models. We compared our algorithms, online IPO and IPO-MD, with recent baselines. To ensure a fair comparison with IPO-MD and Nash MDPG, we will only discuss the results for the online versions of IPO, DPO, and SLIC in this section. We have dropped the online prefix for simplicity. For results on the offline versions of these algorithms, please refer to the appendix. To enhance interpretability and reproducibility, we focused on the contextual bandit case where actions, referred to as generations, are dependent on a prompt. In our experiments, we followed RLHF-style procedures by starting from a supervised fine-tune checkpoint and then further fine-tuning using algorithms such as RL, IPO, DPO, SLIC, Nash MD, and IPO-MD. These algorithms utilize either a learned reward model, RLHF, or a learned preference model, IPO, DPO, SLIC, Nash MD, and IPO-MD. For the implementation details, contrastive offline algorithms like IPO, DPO, and SLIC optimize the policy directly by minimizing specific losses over a pairwise dataset. On the other hand, contrastive online algorithms use a trained preference model to train the policy. Regarding IPO-MD, the main difference from online IPO lies in how generations are sampled. In practice, we sample from a one-step-at-a-time mixture due to the complexity of the ideal sampling method. In our evaluation tasks, we tested all algorithms on an article summarization task using a dataset with pairwise preferences between alternate summaries. We trained our models on a training set and evaluated them on a test set. For training the policies with online algorithms, we used prompts from the XSUM dataset and T5X large language models. The policy model was a large encoder-decoder model, while the preference and reward models were XL encoder-decoder models. Our evaluation process involved using POM2 for side-by-side comparisons of responses generated by different policies. We used prompts from the XSUM dataset for evaluation, following a similar procedure as previous studies. In terms of hardware, we utilized cloud TPUs for our computations. Our experiments were run with default parameters, including a learning rate of 10⁻⁻⁴, a total of 30,000 training steps, and a batch size of 32. We used the Eta factor optimizer with a decay set to 0.8. Section Summary. In this section, we present our experiments on fine-tuning large language models, comparing our online algorithms, online IPO and IPO-MD, with recent baselines. We focus on the online versions of IPO, DPO, and SLIC for fairness in comparison against IPO-MD and Nash MDPG, while offline versions are detailed in the appendix. Our experiments involve RLHF-style setups where we initialize from supervised fine-tune checkpoints and further fine-tune using algorithms like RL, IPO, DPO, SLIC, Nash MD, and IPO-MD, utilizing reward or preference models. Section: Main Results. In this section, we present the comparison scores of various online algorithms for a summarization task. We evaluate algorithms like RL, IPO, DPO, SLIC, IPO-MD, and Nash MDPG. We use the RL algorithm as a baseline for comparison. The RL checkpoint is fixed, chosen after testing different values of tau and comparing performance with the SFT checkpoint. For the other algorithms, we evaluate every checkpoint against the RL checkpoint using over 2,000 prompts. We check every 2,000 learner steps for a total of 30K steps, varying the regularization parameter tau and beta for IPO-MD and Nash MDPG. We select the best checkpoint for each algorithm and run them with 3 different seeds using the best hyperparameters. We conduct 9 side-by-side evaluations for each pair of methods, reporting mean and standard deviation across these comparisons. In the summarization task, IPO performs the best on average in the side-by-side comparison. When considering standard deviation, IPO and IPO-MD's performance are statistically similar, consistently outperforming other algorithms. This indicates their robustness and proximity to a Nash equilibrium compared to other algorithms. These results are specific to summarization, and further experiments are needed to confirm these findings for a general conversational agent. Summarization is a good test for human alignment algorithms due to its complexity and high demand. We also explore the impact of the regularization parameter on IPO and DPO. For small values, IPO and DPO behave similarly, but for larger values, IPO's performance drops faster due to stronger regularization. This aligns with findings showing IPO has a stronger regularization effect as tau increases. Additionally, we analyze the performance of IPO online against RL as it trains. We observe that stronger regularization requires more training time to achieve optimal performance.